I'll just move this over here. So we know that our energy is equal to this. And our energy, the wave of our energy, must have a quantized value and discrete levels. So on the first level, we have only one node, and plug in n equals to 0, our energy is equal to 1/2 h bar omega. For the second energy level, we have two nodes, and plugging n equals to 1, we get 3/2 h bar times omega, and so on, so on. On the third energy level, plugging n equals to 2, 7/2 times h bar omega. I know the drawing is not so good, but this is a picture of what the wave function of harmonic oscillator looks like. As the energy level gets higher, there's more nodes. And when we get to really high energy levels, it's going to look like this. Our wave function starts to model what's going to happen in classic harmonic oscillators. So this is our potential energy curve, where at this point there's really high potential energy, and at this point there's low potential energy. And we can see that there's higher probability of observing the particles at the higher potential energy point over here than at lower potential energy point, because the amplitude makes the probability, and at this point amplitude is lower than this point. And that actually makes sense, because we think about a spring oscillating, and when it gets to the highest potential energy point, it's going to stop and stop briefly. And there's a higher chance, if we're just taking random photo shots, there's a higher chance of observing it maximally stretched than observing at the middle point where there is a highest kinetic energy. So when our energy level actually goes to infinity, so as n goes to like 1000, our wave function actually models our classic harmonic oscillation.